So you take the steering wheel and do like this. And then the tires do like this and the car goes in the direction you want it to go. Pretty obvious, right? Well, yes, on the surface it may seem obvious, but if you look beneath the surface, the things that your tire actually does to make it possible for you to take a turn are not so obvious. In fact, they're incredible. Now, the phenomenon that we'll be explaining in this video will be a bit hard to wrap your head around at first, but there's going to be plenty of relatable, real-life examples to help you do it. And if you manage to do it, I promise that by the end of the video, you'll experience a moment of true enlightenment and a completely new perspective on many things involving driving, vehicle behavior, and cornering speed. So let's start with the basics. As we said, when we operate the steering wheel, the wheels turn. However, there is some fine print here, an asterisk, and it says that the steering wheel does not give you direct control over your tires. What I'm about to say is going to sound extremely obvious, but it's important to keep it in mind in order to be able to understand the concept in this video. Now, when we're operating the steering wheel, we are not able to somehow magically grab the tire over its entire outer surface and then change its direction of travel. Obviously, we can't do this. And because we can't do that, instead what we're doing is that we connect the steering wheel to a small thin rod, which is then attached to the steering knuckle, and then the steering knuckle houses the wheel bearing and the wheel hub, and the only thing attached to the wheel hub is the wheel itself. So what we're doing when we're turning the steering wheel is actually forcing the wheel to deform the tire, and then we hope that deformation leads to the vehicle going in the desired direction. Now, if you have ever been in a car and gone through a corner at some speed, you have probably noticed that there's a force that is getting you to lean in the opposite direction of the corner. Obviously, this is centrifugal force. The same force that makes it possible to do this also wants to run you off the road. You want to go here, but centrifugal force wants you to go here. The only thing standing between you and centrifugal force are your tires, because they're the only point of contact between your vehicle and the road surface. So if centrifugal force wants you to go here, you point the wheels in a different direction and you go through the corner. But there's a catch. When you're traveling at normal road speeds, the direction in which your tires are pointing at any moment in time is not the direction in which your vehicle ends up going. I'm not making this up. It's gonna sound confusing at first, but I promise it will make sense. Remember what we said. We cannot grab the tire over its entire outer surface and rotate it. Instead, we control through the steering inputs, we control the wheel, and then the wheel deforms the tire. But there's a problem. The wheel cannot deform all of the tire equally. The contact patch, or the part of the tire that is actually touching or contacting the road, cannot be deformed by steering inputs during driving. This is because the contact patch is temporarily stuck to the road by friction between it and the contact surface. So what your steering inputs do instead is that they twist the rest of the tire around the contact patch. You can visualize this using any flexible rubber item. When you press it into a surface, the part that touches the surface becomes the contact patch. If you twist it, you will see that friction keeps the contact patch in place, but the rest of the rubber item twists and deforms around the contact patch. So when you make steering inputs, the direction in which your tire and wheel point changes, but the direction of the tread in the contact patch stays the same. Now, during the very brief point of time that it takes the tire to roll through this contact patch, the tire is actually heading in the direction of the contact patch and not in the direction in which you pointed the tire and the wheel with your steering inputs. But because a tire is rolling forward, it means that the treads which you deformed or deflected with your steering inputs will all eventually end up in the contact patch too. But the catch is that once they land and become the contact patch, the fact that they are deflected means that they hit the surface offset and pointing in a different direction from the previous contact patch. It can help you wrap your head around this by imagining how the tire is actually stepping or walking laterally by putting down each subsequent contact patch laterally offset from the previous one. The hand on the ground is the contact patch, and the hand above is the incoming tread. As the incoming tread becomes the contact patch, it lands offset from the previous one. Now, as you progressively add more steering input, you keep twisting the tire in relation to the current contact patch. This means that the next contact patch also lands offset from the previous one. This continues and allows you to take a corner. But this also means that if we observe the tire at any point during the corner, the tire is never actually heading in the direction in which you pointed with your steering inputs. The tire is always heading in the direction of the contact patch because it's contacting the road and rolling through only the current contact patch. All the other future contact patches are in the air. Now, the difference in direction, or the angle between the direction in which you point the tire and the direction in which the tire is heading during that moment, is called the slip angle. Now, the name is a bit confusing, and it's important to understand that the slip in slip angle doesn't mean that the tire is slipping all over the place and that the vehicle is drifting. What the slip refers to, it refers to the fact that each subsequent tread element or contact patch gets slipped laterally ahead of the previous one. It's the slip between the direction in which the tire is pointing and in which the vehicle is actually going in that particular moment. Despite what some videos on YouTube may try to convince you, slip angle is not a driving technique or a secret trick to speed used by, cartoon characters and legendary racing drivers. In fact, slip angle isn't even optional. It's mandatory. And that's because without slip angle, it would be impossible to take a corner at pretty much any speed. And this is because as each subsequent tread element gets slipped ahead of the previous one, we generate a force. This slipping creates a force known as cornering force. And cornering force is what actually gets you through the corner. Without cornering force, you can't go through the corner. Now, if slip angle is 0, then cornering force is also 0. If slip angle is 0, it means that you're going perfectly straight. The nice thing is that we can easily observe cornering force. And here it is. Now, here we can see centrifugal force trying to push the vehicle out, trying to run it off the road in the direction of the outer part of the corner. And here at the bottom part of the tire, we can see cornering force grabbing onto the road and fighting centrifugal force. In fact, cornering force is generated by each subsequent contact patch landing and grabbing the road surface laterally offset from the previous contact patch. This cumulative grabbing of the contact patches stacks up and creates a cornering force. And here we can see that the vehicle successfully takes the corner along the desired path because cornering force is higher in this case than the centrifugal force and the momentum of the car. This means that the higher the cornering force, the faster we can go through a corner. Now, centrifugal force and vehicle momentum are a consequence of vehicle speed. The faster you enter a corner, the greater the incoming momentum and the greater the centrifugal force once you start turning. But if you have high enough cornering force, then you can resist more centrifugal force. In other words, the more cornering force you have, the more speed you can throw into the corner and carry through the corner. Now, you might be thinking that this whole cornering force thing is just nonsense. It's just a different word for friction and grip. This is not cornering force. It's tire, friction, and grip keeping the car in its desired direction of travel. In reality, that's not the case. Cornering force and friction are two different phenomena. They're not the same thing. They're very much connected, but they're not the same thing. And what I'm about to say is not scientifically correct, but it will help you understand this. Friction is sort of a passive force, and cornering force is an active force. Friction only resists movement. Friction is what keeps your car in its place when you go up a hill and pull the handbrake. But cornering force is an active force because it generates lateral movement. Friction cannot generate movement. Cornering force is the active, laterally offset biting into the road of each subsequent contact patch. Each subsequent contact patch could not grab and hold onto the road without friction, but friction alone cannot generate a lateral movement. This is done by the deflection and the flexing of the tire, which enables lateral movement and thus cornering force. Now this is where things get really interesting, because all tires have an optimal slip angle, the desired slip angle at which they generate the highest cornering forces and allow for fastest cornering. Slip angle itself is not a driving technique. We all rely on the slip angle for the ability to take a corner. What sets amazing drivers apart from average ones is the ability to use higher slip angles longer and more consistently. Fortunately, the relationship between slip angle degrees and cornering force can be displayed on a graph, and the line looks something like this. The first thing we can observe about this is that the relationship is not linear. If it were linear, it would look something like this, and cornering force would be increasing all the way up to a slip angle of, let's say, 90 degrees. Of course, this is impossible because it would make cars capable of taking perfect 90-degree turns at blisteringly high speeds and, probably annihilate the suspension, and the G-forces would, kill anyone inside the car. We of course know that this is impossible. It never happens in reality. This is imagination, but physics does not reflect imagination. It reflects reality. And therefore the graph looks like this. We can observe that cornering force rises rapidly for the first few degrees of slip angle. This of course makes sense because the greater the slip angle, the greater the difference in angle or the offset between the current and the subsequent contact patch. The greater the angle at which the subsequent contact patch bites into the road, the greater the rate at which it pulls the tire laterally, and the greater the resulting cornering force. But of course, tires, like any other material, have their limitations, and they can only take so much twisting and deflection, and this is why cornering force peaks at about 5 to 6 degrees of slip angle for normal road-going tires and then gradually starts falling off. Racing tires, on the other hand, are capable of achieving higher cornering forces at higher slip angles. However, their cornering force falls off more rapidly as slip angle increases. In other words, racing tires can achieve higher peak cornering force, but can only maintain it over a shorter slip angle range. This tells us that tire cornering force depends on tire compound or material, as well as size and construction. Racing tires may be capable of higher cornering forces, which allows greater cornering speeds. However, in order to be able to sustain higher levels of twisting and deflection, racing tires have to be made softer and more flexible, and this then results in a reduced lifespan compared to standard road-going tires. This graph also explains why you have to take sharp corners at very low speeds. A sharp corner requires a lot of steering input, in other words, high slip angles. And as you can see, at high slip angles, cornering force is reduced. And this is why you have to reduce your speed in order to reduce your vehicle's momentum and resulting centrifugal force, in order to prevent them from overpowering your already reduced cornering force. And this brings us to driving technique. Now, slip angles and slight four-wheel drifting became synonymous because many legendary racing drivers developed a technique which involves a bit of drifting through corners. Now, that is a consequence of constantly trying to stay within this portion of the graph right here, and doing that is very hard. Fact is that the highest possible speed through a corner is achieved when the highest possible vehicle momentum and centrifugal force is overcome by the highest possible cornering force. As drivers are constantly trying to achieve that state, they of course from time to time inevitably go over the limit. And when you go over the limit a bit, without going too much over the limit, cornering force gets slightly overpowered by centrifugal force or vehicle momentum, and the car drifts a bit. However, the important thing is that going over the limit a bit is faster than staying under the limit. Amateur drivers most of the time stay well under the limit because that is what our instinct for self-preservation is telling us to do. But by staying under the limit, we usually allow cornering force to overpower centrifugal force and momentum by an overly large margin. Fact is that a lot of speed remains that could be thrown into that corner. And this is why approaching the limit is hard and takes practice. Also courage. But staying on the limit is a lot harder and can be considered an art form to constantly stay within this very tiny margin. I'm sure that even a supercomputer would have great trouble finding the perfect set of vehicle inputs that achieve the perfect balance of all of these forces at every point in the track. And this is why being truly fast is truly hard and requires talent followed up by endless practice. Now, if you don't have talent, you can always get a lot of big spoilers. Spoilers can increase your cornering force. And this is because by increasing the vertical load on the same tire, we increase cornering force at every slip angle for that same tire. Now, vertical load is basically how hard we push the tire into the road surface. The harder we push the tire into the road surface, the greater the friction. The greater the friction, the greater the road holding capacity of each subsequent contact patch. Now, spoilers act as big barriers for the incoming air. As the incoming air overcomes that barrier, it has no choice but to push down on that barrier. And because spoilers are connected to the car, the whole car gets pushed down and vertical load on the tire increases. This is why Time Attack and other racing cars have giant spoilers. They want the maximum possible cornering force so that they can throw the maximum speed into every corner. And there you go, tire deflection, cornering forces, and slip angles. Things that we usually don't give too much thought, but things without which the only path through a corner would be straight and off the road. So there you have it. That's pretty much it for today. As always, thanks a lot for watching, and I'll be seeing you soon with more fun and useful stuff on the Deformation.